Right. So today for temperature, mostly what you will see questions from is this. This is one of the topic. Energy change with change in state. This is something that you can mark for yourself. Um, then all of the state diagram. This is something that can come your way. Heat capacity. This is something that can come in your question paper. This is a question that I have seen to be a decent, good maths question for the temperature topic. You can mark the paper code for this. This is a good one. And yeah, so heat capacity question, that is the maths. Then you have state changes, how potential energy and kinetic energy changes with different states. That's something you will look into, which is important. And a bit of temperature scale or the Kelvin scale. This is something you need to understand as well. And I'll get into that as well. Right? Okay. Sign in. Okay. So first I will start off with the boring stuff, which is what temperature really means, right? And a few of different types of thermometer, which you may have come across at some point in your life, but I'll still get over these. So the first thing is, how do we define temperature, right? And for that, you need to understand the concept of kinetic energy. What is kinetic energy? Ke. It is simply the amount of motion energy any object or atom has. So, rotational motion, translational motion, any sort of motion energy that an object has is the kinetic energy. If I have this piece of metal, let's call it the calcium metal, Ca, right? And I heat it up, what happens? The body or the material itself is not going to move around. It has a bunch of atoms inside, and this gains energy. The atoms gain energy, and what essentially happens is the atoms, the electrons, move around. The atoms will vibrate, electrons will translate or move around, right? Free electrons move around, they gain kinetic energy, and they will also have rotational motion or rotational kinetic energy. Okay, so a couple of things that will happen. Okay, so the Slido code is 2321508. So if you have any question, you can put it down over there, right? That's the code. So, anyways, now as I was saying, kinetic energy. Yeah.
What's that code for again?
Sorry. That
What's
is
that?
for Slido. So if you just want to ask a question or something, and if I ask you guys a question, you will essentially be putting it over here. So I'll put up a poll, or if you have any question, you put up in Q&A. Right? That's it. But I don't think I'll ask any question for this session because there's not too much maths involved with the temperature topic. You get that in ideal gases and thermodynamics. One of the worst chapter for a question. The reason I say that, some of the most difficult questions in the history of A-level physics exam have come from thermodynamics chapter. And I'll show some of you. I also have one video which you can look into where we have discussed really, really difficult questions. So that's really good. Coming back to what I was saying, kinetic energy. Now, as I heat this calcium bar over here, what happens? The atoms inside gain rotational or translational kinetic energy, or the electrons itself. That is how this calcium piece of metal will raise its temperature. Raise its what? Temperature. So whenever your temperature is increasing, you know the atoms inside are gaining kinetic energy. The electrons are moving around more. So that motion, rotational, translational, whatever it may be inside the atom, is essentially an, an indicator of how high the temperature is. So when you see, okay, I have a piece of metal over here, and I have another piece of metal over here, and I see that the temperature for this is 10 degrees Celsius, and for this it's 20 degrees Celsius. My understanding is the atoms, the electrons inside the piece of metal over here has way more kinetic energy. That is what I understand. You will very soon understand or know about an equation that is Ke is equals to 3 by 2 kT. This is the formula of kinetic energy, and you will understand this, see the derivation of this, good, beautiful, pretty derivation for this, and you'll understand how closely kinetic energy is actually related to temperature. So temperature is nothing but a measure of kinetic energy. So whenever you have the temperature being denoted by a thermometer, that is telling you how much kinetic energy the object has. That is all it's telling you. And that is the first fundamental concept you guys need to have. That temperature is a measure of kinetic energy. That's it. So how do you define it? If they ask you to define in your 1 mark or 2 mark question in your paper, where you say it is a temperature is a measure of the average kinetic energy of the particles making up the substance being examined. Okay. So what if I measure, whatever I get the temperature of, that temperature denotes the material's kinetic energy. So if that is what temperature is, what is heat? We've talked about, understood heat energy, right? And essentially what that is it is simply a form of energy. It is a type of energy. That's the first thing that I can tell you guys. And the second thing is whenever there's a transfer of energy due to difference in temperature, we say heat energy is being transferred. What does that mean? If I have one object over here, that is, let's say, copper, and over here I have iron. Or let's say I keep this copper as well. It doesn't matter what type of material it is, right? Let's not overcomplicate it. So I say I have kept these two different separate blocks attached. I've put them in contact. Now, before keeping in contact, copper had a temperature of 30 degrees Celsius, and this copper, the second one, had a temperature of 10 degrees Celsius. Now, due to this difference in temperature, I will have what flowing? Heat. Energy will be flowing from what is a high temperature to what is a lower temperature. Due to that temperature gradient, we call this a temperature gradient, due to there being a difference in temperature, what we see is what is warmer allows heat for being transferred into a colder region. 10 degrees Celsius in comparison is a colder region. Hence, we have heat being transferred from the 30 degrees Celsius to 10 degrees Celsius. Now, due to having a temperature gradient, we have a transfer of energy, and this energy we call heat. This is the distinction between heat energy and other forms of energy, whichever you want to think of electricity, electric energy, or
Um,
whatever you're talking about. Yeah.
sir, do we need to know why it's transferred from a region of higher temperature to lower, or no?
Do you need to know why it transfers from high energy to low energy? Is that what you're asking?
Yeah, yeah.
I mean, not essentially. They won't ask you anything like that. But I mean, the reason is simply that you can talk about density, you can talk about diffusing the electrons with higher amount of energy. They want to diffuse into an area with lower amount of energy. So you can talk about that, but essentially that is the only reason. It's entropy. If you want to get more into the specifics of it, which you guys will learn in chemistry, I guess, it is simply entropy, and energy wants to distribute itself. That's the more technical side of it. Do you need to know? If you study chemistry, yeah, sure. But if just for the syllabus, no.
All right.
Got it? Okay. So yeah, the technical answer is entropy, and in general, you can say energy wants to diffuse itself into an area with lower energy. Okay. Great. So we understand one thing, that is temperature. What is the definition of temperature? It is a measure of kinetic energy. First thing. Second thing is what is heat? Heat is simply a transfer of energy when we have a temperature gradient. When we have a difference in temperature, high amount of energy wants to go to a region with a lower temperature. So it wants to diffuse itself, right? So that is where we have a transfer of energy called heat. These two things we have clarified, the fundamental part for this chapter. And the next few things, one, two, three things that I have, uh, four really. So the four things we have, quite boring. So bear with me. And this is, does this come much in your syllabus in the paper? No, if I were, in a time crunch, if there was one thing to skip, probably this is what I would skip. But you guys have time, so you guys should definitely study, right? Which one you shouldn't skip, I will say. That is the last part, the energy thingy. I'll run over those a bit more. Okay. So the first one, you guys must have heard of or learned about liquid in glass thermometer. So the mercury thermometer you have at home, if you do, I don't know, uh, that works on the basis of the mercury expanding. So when there's heat, the mercury gets heated. Just like any other material, it expands. Now, due to it expanding, we understand that the temperature is rising. And that rising of temperature, rising of volume of mercury, or it occupying more space in the thermometer, is an indication of temperature rising. And we can quantify that increase in temperature by calibrating it. And we understand, okay, if mercury increases from this much to this much, we can quantify it into saying, okay, this must be a 20-degree Celsius increase. If it increases this much more, I understand it's a 40-degree Celsius increase in temperature, right? And this is a thermometer, right? So that is how we understand by the movement of mercury in the thermometer, by its expansion, that temperature is rising, and we quantify that into saying, okay, it's 23 degrees Celsius, 30 degrees Celsius, whatever the measurement may be. Great. So how can I explain that in more details? First thing you need to understand when I'm talking about a mercury thermometer, look at this image. This is a mercury thermometer. What are the features of a thermometer? If I just draw it over here, uh, right? This is the body of the thermometer. This is called the bulb of the thermometer. And right inside, you have, consider that red line to be mercury itself. So essentially, or the line, the temperature line. So essentially, what happens is this bulb is filled with mercury, and whenever you put this bulb inside anything that is warm, cold, whatever it may be, the mercury expands, gains the heat, gains the heat, and it will start expanding. Similar to anything that you see around, any liquid that you see, any solid that you see, if you start melting it, it starts occupying more space. Why? The spacing inside the atom increases, right? They gain more energy, they start wanting to occupy more space, right? So that is why it expands. The material expands when heat is provided to it, when temperature increases. Similarly, with mercury, it increases its temperature and hence it expands, right? So if the mercury is in room temperature and you're measuring something above room temperature, then the mercury will expand. And your body temperature, which is probably 37 degrees Celsius, is definitely above room temperature. So when you have a fever, that's why it works. Now, if you had to measure something that is below room temperature, well, that would be difficult. That would be difficult. Okay, and for that we have different sorts of temperature thermometers, sorry, and we will look into those as well, how they give more accurate or a larger range. We will discuss all this. What are the advantages and disadvantages of certain types of thermometer? So essentially, you understand how the mercury thermometer works. It gains energy, starts expanding, and rises up over here in the body of the thermometer. Wherever it stops is the temperature reading, right? So now, if I get back to the features we have, first thing, what is a thermometric property? First, understand what a thermometric property is. What is it? So, what about the mercury is explaining or telling me what the temperature is? What is it about the mercury? It is its volume, the volume it occupies. So, in this thermometer, what is telling me the temperature is the increase in volume or the increase in length, whatever you want to say. So in this line, there's this thin line that you have inside the body. There's a space inside. There's one line of space, right? Inside, it's a very thin line of space through which the mercury expands. That space denotes the volume that the mercury occupies. So the thermometric property over here is the volume. Why? Because based on whatever the increase in volume is, I get to understand what the temperature is. Higher it goes, more length it occupies, or more volume it occupies, the higher the temperature is. So, what is the thermometric property? Any property that denotes what the temperature is. And that property over here is volume or the length, whatever you want to say. Both are technically accurate. Volume is more accurate in nature, but we also obviously you can say, okay, I'm measuring how high it goes in length. That is also an accurate description. You can also say how much volume it occupies, and that is also an accurate description of what's happening. Fair enough. So that's a thermometric property. And what is the material that we are measuring? Mercury. Mercury is our main material inside the thermometer, for which, if we provide some heat, gains the energy, increases the temperature. So mercury is the substance we're working with. Now, when is the final reading taken? When thermal equilibrium is established. There is no longer a temperature gradient between the bulb and the liquid inside, or any solid that you're measuring, anything, any material that you're measuring the temperature of. There is no longer a temperature gradient between the bulb and the liquid itself or the material that you're measuring. What does no temperature gradient mean? If bulb is 10 degrees Celsius, my liquid should also be 10 degrees Celsius. Now, does that mean if my body has 37 degrees Celsius, the bulb will now gain the heat, gain the energy, and the bulb's temperature will rise to, let's say, somewhere like 30 degrees Celsius, and the temperature of liquid will decrease to 30 degrees Celsius to compensate for the increase in temperature from the bulb. Will this happen? Yeah, go ahead. Did you want to ask something?
So could you repeat this again? This part I didn't understand.
As in the temperature gradient part?
Yeah, yeah,
Yeah?
yes.
Okay. So what I'm saying over here is, when do we finally take the reading of the temperature? We take the reading when the temperature of the bulb is exactly the same as the material of which we're measuring the temperature. Okay, so if my body temperature is 37 degrees Celsius or 38 degrees Celsius, when the thermometer reaches thermal equilibrium with my body's temperature, the thermometer, if it's an electric thermometer, it will beep. That no longer my bulb's temperature is rising, hence I start beeping. And that's when you understand, okay, thermal equilibrium has been reached, and the thermometer now reads exactly what the body's temperature is. So when
So
the energy transfer stops, that is the thermal equilibrium. And that is when the temperature between 2 points is same. Do you get that?
but like, aren't we using the thermometer to find out the temperature of the solution?
Yes.
How will we know what the temperature of the solution already is for us to reach that?
When the temperature stops rising. So it will stop,
Oh,
right?
okay.
So before that, in chemistry, what do? When you do practicals, if you guys have done the practical exams in chemistry, you guys have this experiment,
Temperature
which I
varies.
remember doing.
Yeah.
Exactly. So whenever you see that the temperature peaks out at some temperature, and now, okay, now the temperature starts falling because it's losing its energy to the surrounding. So that peak essentially is the temperature of the solution. Do we get that? So it
Oh,
stops. The energy transfer stops after a point, right?
all right.
Okay. Right. So now what I was posing to you guys was a bit of a thought experiment after understanding that, okay, thermal equilibrium has been reached when energy transfer stops, and that is when we take the measurement. That is when we take the final reading, when the temperature stops rising. But the thought experiment I was giving to you guys right now is that, well, if my liquid itself is at 37 degrees Celsius, right? And I'm telling you guys that, okay, the mercury was at room temperature, let's say 25 degrees Celsius. Now it will gain energy, it will gain temperature, right? So if it gains that temperature, shouldn't it take some of the energy from the liquid, and wouldn't the energy of the liquid decrease to, let's say, 30 degrees Celsius? Just assumption. So if that happens and my thermometer gains that 5 degrees and increases to 30 degrees Celsius, so isn't this inaccurate though? Because while measuring the liquid lost its energy to the bulb, right? So what do you think really happens in real life? Is it something that happens? Or if it doesn't happen, why do you think it doesn't happen? I want to ask you guys. You can answer in Slido. I've opened an answer poll. You can answer there or unmute and tell me. Why do you think, or if you don't think, that the temperature of the liquid doesn't change? Because if it changes, that's bad. That's pretty bad. Then I'm not getting the accurate temperature reading of the liquid. So if it's 37 degrees Celsius of the liquid and it decreases to 30, that is inaccurate reading. But do you think that this happens? Do you think the liquid itself loses its temperature to the bulb for the bulb to gain that temperature to 30 degrees Celsius? Do you think that happens? Just answer below. Anything that you can think of. Or just let me know. Unmute and let me know. I'll give you guys 1 minute. Why do you think it happens or it doesn't happen? Is the question clear to you guys? Do you understand the question? My question is, does the liquid lose its temperature in the process of thermal equilibrium being reached? That's my question. Okay.
If I say, for example, the liquid loses the temperature of the liquid decreases,
Yeah.
that temperature I can say is going to mercury, right? Like the
Yeah.
subject is mercury.
The energy is transferring to mercury, yes. Which is why the temperature of the liquid is decreasing. But do you think that happens? Is my question.
Okay.
So my question is, do you think the liquid really loses that much energy that its temperature falls? Yeah. So, a person said that the liquid loses temperature while the mercury increases. So my question is exactly this. Do you think the liquid really loses temperature or it stays constant? And if it stays constant, why? And if it loses temperature, then we know why. But my question to you guys, do you think the liquid really loses temperature or it does stay the same? That is my question. Because if it loses temperature, we have a problem. And we are not getting the right measurement. Because while trying to measure, the liquid is losing the temperature. I'm not getting the right reading. So what do you think happens over here? Do you think the liquid loses temperature? And if it doesn't, why? I'll take one more response and I'll give you guys the bit of the answer.
I think it does
Yeah,
lose, but the loss is like very small. It's almost negligible.
right. So that's why you think the temperature doesn't change, even though there's a
Yes.
bit of. Okay, great. So with that, I'll tell you guys, and what you said right now is very accurate. The reason, yes, there's an energy transfer for sure, without a doubt. But what really happens is the amount of mercury inside is very little. So the amount of mercury inside is very little, which is why it requires very little energy to gain that temperature as the liquid itself. So since we have a large amount of liquid, that is also why, not in all places, but in a lot of cases, good experiments, they will tell you you should be working with ample amount of liquid such that if it has 37 degrees Celsius, the temperature will not decrease because the amount of liquid is so much. that if it gives a little bit of energy to mercury for its temperature to rise, that is no problem. Do you guys remember E is equals to MCAT formula? I call this MCAT. I mean, it's basically mass times heat capacity times change in temperature. So notice over here that for the mercury to reach 37 or 37 degrees Celsius, if it has a lower mass, which it does, I'm telling you guys, mercury over here in the thermometer is very little bit of mercury, and its heat capacity is low. And by the way, it does. Heat capacity is low for mercury. And if these two things are low, then the energy required is what? Less, right? The energy required is less for the mercury. And the liquid, let's say if it's water, it has a high heat capacity. Remember, guys. So liquid, for example, water has a high heat capacity. And when you're working with a larger mass, so for the liquid, my mass is large, right? And its heat capacity is large, let's say. So for the same change in temperature, if I'm talking about 1 degree change in temperature of the liquid, I need way more energy, way more energy. So if my liquid just loses 1 joule of energy, the temperature will not change. While this 1 joule of energy goes to the mercury and it can easily raise the temperature to whatever the liquid is. So when the thermal equilibrium is established between mercury and the liquid, then the temperature stops rising because the energy stops flowing. So let's say 1 joule of energy from the liquid goes to the mercury and the temperature rises to 31, and then okay, thermal equilibrium has not been established. So what do we do? One more joule goes, and it increases to let's say 32. And then okay, we see it's 32 and 37, and it's different. There's a thermal gradient over here. More energy is needed. One more joule goes. This keeps happening until and unless this temperature becomes exactly 37. And while this increase is happening, the liquid's temperature does not decrease. Why? The amount of energy that is going is very little as compared to the amount of liquid you have. Notice the mass over here in the equation, right? So this is a bit of analysis that I wanted you guys to think of, right? A bit of conceptual question, right? Fair enough. So that is why you will see the question may come, may not come. Why do we have little mercury in the thermometer? What would happen if the amount of mercury increases? This is a conceptual question that can come in your paper. I'm just saying randomly, arbitrarily. I'm just putting it out there. Can come, cannot come. I don't know, but that is the concept, right? So the amount of matter matters. Great. So how do we calibrate this? This is a simple part. You may have studied this in O levels at some point. What do? I take the thermometer. I put mercury in the bulb, and I put the thermometer in the 0 degree. So basically, we take two extreme points. One is 0 degrees Celsius, and the other is 100 degrees Celsius. So at 0 degrees Celsius, what do we see? Okay, the amount of mercury rises till this point. Why can't we see the mark? Okay, so the amount of mercury rises till this point. So I go on to my mercury's glass body and say, okay, this is the mark for 0 degrees Celsius. If I have 0 degrees Celsius, my mercury from the bulb increases its volume to occupy this amount of space. So this portion becomes my L naught, my initial length, and that is my 0 degrees Celsius. And then I see that I put the thermometer in a, let's say, higher temperature, right? That is 100 degrees Celsius. These are both known temperature. We know what is 0 degrees Celsius. We know what is 100 degrees Celsius. 100 is basically the melting point for ice, and zero is basically, sorry, 0 is the melting point, and 100 is the boiling point, right? So we know these two extreme points of liquid. So we just put the thermometer in these two known temperature, and we take the mercury reading. So in 0 degree, what do? We take the length, we mark it, and call it 0 degrees. I put the thermometer again in 100 degrees Celsius, and I measure how much length it has now occupied, and I measure this part as 100 degrees Celsius. Now what do? I know the two extreme points on the thermometer. I now divide the space in between equally, 100 divisions, let's say. So now this space gets divided in 100 divisions, this entire space. So now I have a thermometer which is calibrated. So I have it marked over here. So when I put this inside our body or inside liquid, whenever the temperature rises, I can measure it against the calibration and say, okay, this is 37 degrees Celsius. This is 40 degrees Celsius. That is essentially how it works. And this is how the graph may look like. So at 0 degree, you mark L naught, which is, let's say, this L naught is probably, let's call it 10 centimeters. So 10 centimeters I mark as 0 degrees Celsius. And then I mark, okay, the LF final length is, let's say, 60 centimeters. And I mark 60 centimeters over here for 100. So this line is now describing how the mercury expands with respect to temperature. Okay, this line now explains how the temperature changes with respect to length or vice versa, right? So this is basically, and the other reason we use mercury is mercury expands linearly. What does that mean? This is something that you may have heard of. So mercury expands linearly. What this means is if to go from 0 degrees to 1 degree Celsius, mercury expands. So 0 degrees to 1 degree Celsius, mercury will expand 1 centimeter. Similarly, to go from 1 degree Celsius to 2 degrees Celsius, it should also expand 1 centimeter. Now, what happens in case of other material? If it goes from 0 degree to 1 degree, it probably occupies 1 centimeter. But then going from 1 degree to 2 degree, it probably occupies 1.5 centimeters. Now, this is a problem. This is not a linear increase. And mercury, if you notice, has more or less a linear increase in its volumetric property, which is the volume, right? Sorry, not volumetric property, thermometric property. So its thermometric property is the volume or the length. So that length increases linearly with temperature. Every 1 degree increase in temperature, there's a 1 centimeter increase in length. I'm just arbitrarily putting the numbers up. I don't know. I'm just saying, I'm just explaining to you guys. Now, on the other hand, for other materials, let's say alcohol is still good, but like other, let's say liquid metals or something, for them, what really happens is to go from 0 to 1 centimeter, then again from 1 to 2, 1.5 centimeter. This is not a linear increase. And when you draw the graph, it will probably be something like an x squared graph, some sort of curve. And this is not ideal because I cannot calibrate this over here. Calibrating such a thermometer with a non-linear thermometric property is difficult, which is why we always standardly use mercury. Do we get that? Great. So that's the benefit of using mercury, right? I hope we understand that part. Simple bits till now. Now, next thing is benefits of thermometer. Okay, over here I've rewritten this. Mercury expands uniformly with the temperature, and reading can be taken instantly from the scale. So as you look on the body of the thermometer, you can see, okay, it's risen till this point, and the calibration says 37. So it's rapid. And what is a demerit or a disadvantage of a thermometer, mercury thermometer? The problem is the range is little. Towards the beginning of the class, I told you guys that for the thermometer to work, it has a certain limitation. Let's say 0 to 100 degrees Celsius. So I need to increase the length of the mercury. Oh, sorry, I need to increase the length of the thermometer itself for the mercury to be able to rise to different temperatures or higher temperature. So I can have 1 meter long thermometer. That is not viable. That is not feasible, right? Is that feasible? No. So essentially, the thermometer in general mercury thermometers have a very little range or a shorter range as compared to other options that we have. So the range of temperature of reading that we can have is less, and that is a disadvantage. Because when you have extremely high temperature, the mercury will want to expand outside of my thermometer itself, right? And that is not ideal. Thermometer may also burst. That's not ideal, right? Fair enough. So that's a demerit of having a mercury thermometer. Now, thermal energy is the same as, I mean, I can just read it out for you guys. It is defined by the energy of a substance due to its temperature. And thermal energy transfers between a region of higher temperature to a region of lower temperature. Now, before you ask me, is it the same as kinetic energy? Yes. Technically speaking, thermal energy can be said to be the same as kinetic energy. It is the same definition, it's the same thing. Whenever you have high kinetic energy, that also means the material has a high thermal energy. So it has greater amount of heat for it to transfer, right? Whenever you have high kinetic energy, that also means it has a high thermal energy. So it's the same thing essentially. It's just a different word over here that we use in different contexts. That's it. But it is the same as kinetic energy if you guys are confused. Great. The next one that we have, okay. So that is volume of gas thermometer. This one we don't see as much, but this is also used, definitely. And over here, what is the thermometric property? What we measure is the pressure. So we basically, if you look over here, we plot pressure against temperature. So as the pressure increases, we calibrate the temperature as a linear increase to pressure. So as pressure increases, temperature also increases. Okay. Now this is an innate property that have you guys? I'll teach you guys this as well. But have you guys seen this equation? PV is equals to nRT. Have you guys seen this? Thumbs up if you guys have this equation, ideal gas equation. Great. So you see this equation over here, right? And this equation shows you what? That there's an innate relation between pressure and temperature. And we can use that property as well. We can use this property to make a thermometer. So we can say that pressure is proportional to the temperature. So using this property, what do we do? Using this property, we make a thermometer. So we say that there's a linear proportion between pressure and temperature. How? I mean, you don't need to know the technicality of how the thermometer works, but it's simple. What is it? We use Charles' law, which says that the volume is proportional to temperature, or you can say the same thing about pressure as well. Pressure is proportional to temperature. We saw the ideal gas law, right? PV is equals to nRT. So if volume is proportional to temperature, pressure is also proportional to temperature. Same thing essentially, but what we see is as the volume increases, the temperature increases over here. So when we have, let's say this gas, right? If you guys are following me, this is the gas over here. And what happens is if I, let's say, have a high pressure over here, then the amount of mercury displaced, or I mean, it doesn't need to be mercury, it could be anything. Mercury is not the conversation over here. Don't get confused about our last topic. That is mercury thermometer. Mercury is not relevant over here. What is relevant is as the temperature goes up, the gas will expand, right? Pressure will increase, hence causes the mercury to be displaced by a height. What does that mean? What does that mean? So when I have this gas over here, and I, let's say, provide a certain temperature, right? Provide a certain temperature, increase the amount of heat, let's say, then what will happen? As I increase the temperature, the gas expands. The gas wants to expand. So what does it do? It pushes down on the mercury. Again, mercury is not the conversation over here. Could be anything, doesn't matter. So what essentially happens is the gas wants to expand due to the heat, and it applies a pressure on the mercury, what that does is it displaces the mercury over here to increase the difference in height over here. Okay. So if you have seen in all of us, you must have studied that, you know, YouTube's over here, and you guys have some liquid over here, and it is connected to a gas supply. And when you have a greater pressure, it increases the height. What that means is the pressure is greater, right? So essentially the same thing happens over here, but with respect to increasing temperature. I increase the temperature over here, gas wants to expand and applies a force over here on the mercury, and it displaces the mercury such that the height over here increases. It's just that. It's just that. Okay. So over here, what are we using essentially? The relation between volume and temperature, or pressure and temperature. So you can denote it as Charles' law, which talks about the proportionality between volume and temperature. Okay. So that is what we are talking. Any of you guys, if you're confused, do let me know. Right? This doesn't explicitly come in your questions, that how the, what do you call this, volume of gas thermometer work. That is not going to come. They may ask you the relation of volume and temperature, but that is related to another topic again. So you guys need to know that volume and temperature is related. Essentially, that is the conversation. Okay, that is what you guys need to know. So again, how do we plot it? So as the pressure increases, so as volume increases, the pressure applied in this pipe is increasing. So pressure increases, right? And the amount of height displaced increases. So that is my relation over here. As the height increases, I understand that the pressure being applied also increases. Have you guys read that topic in O levels, probably IGCSE, where rho GH, that's an equation you guys work with, right? And you guys see, using that, you guys understand how much pressure I have in the tube. So as the height increases, the answer, or the pressure, increases. Rho GH. That's an equation you guys must have come across by now. But the point I'm trying to make here, and you guys don't need to know this, if you guys have forgotten, that's not a problem at all. Point I'm trying to make is, as the height increases, that denotes the pressure has increased. Why has the pressure increased? Because volume wants to, sorry, the gas wants to expand, occupy more volume. So volume wants to increase. And why does the volume want to increase? Temperature. This is how, through a cycle, everything is related. So essentially, I know plot, due to knowing the height, I can find out the pressure. So now I plot the pressure and the temperature. So I basically, once I need to calibrate this. So with known temperature over here, initially with known temperature over here, I calibrate this entire system. So I put in, let's say, 30 or 10 degrees Celsius, and I calibrate the entire system. So I see that for 10 degrees Celsius, the height over here is, let's say, I don't know, 10 centimeters. And by understanding that it's 10 centimeters, I find out using rho gh or whatever relevant equation there is, I find out the pressure. So I know the pressure for 10 degrees Celsius, and I plot a point over here. Next temperature for 30 degrees Celsius. What do I do? Same thing. I put 30 degrees Celsius over here. I see the increase in height over here, and using the height, I find out the pressure, and I plot the pressure over here. 2 points I found out. Now I draw a line. Now I do what? I draw a line. Now I have the perfect calibration over here. So for every temperature now, I can find out what the pressure is. Right? I can find out what the pressure is. Or for every pressure, I can find out what the temperature is. Vice versa. Right? So essentially, now if I have an unknown temperature over here, right? Unknown temperature, I can find out the increase in height. And by that, I know the pressure. And by the pressure, I find out what? The temperature. So let's say I find the pressure to be somewhere over here, right? Using the height scale over here. So now using that pressure, I find out, oh, okay, so it must be 15 degrees Celsius. That is how it works. It's a lengthy process, and you will see that in the disadvantage and advantage table. Okay, so this is a lengthy process. Now, benefit, this can measure a wide range of temperature. That's the benefit of it, right? So I can, if I have a large scale over here, using that, I can measure a very large range of temperature based on whatever scale I have. Okay, so however much pressure I can measure, based on that, I can also measure the temperature. No worries. So the range of temperature I cover, greater. Secondly, what's a demerit over here? The readings have to be taken from the graph, as mentioned. So it's a lengthy process. I need to first find the height, I need to calculate the pressure. Using the pressure, I use the graph to find out where my temperature is, what my temperature is. So do we get that? It's a lengthy process. That's it. And I explained to you guys how using the height, we find out pressure, use the pressure, use the graph, I find out the temperature. That's how this works. And this can be automated, of course, but this is the manual working of it. Great. So you guys now know two types of temperature thermometers. Third type, less relevant, but when you guys study electronics, engineering, those stuffs, you will come across this the most. And this is a resistance thermometer. You guys have heard of thermistors, right? Uh, and this is very related to that. This concept is very related to that. So essentially, wait a minute. Okay. So essentially, what happens in case of a resistance thermometer is the resistance is proportional to temperature. This is something, again, I asked you guys to recall from IGCSE, most likely, that as the resistance increases, probably in AS as well, but as the resistance increases, the temperature increases. Or I can say the opposite, that when in a material you increase the temperature, the flow of electrons get hindered. What that means is the resistance in the material has increased. Due to a higher temperature, due to the atoms vibrating more, the material has higher resistance. And that is a relation that we're going to work with. So wherever you get the trend over here with the thermometers, using a formula, we find out, okay, temperature is related to this property. Can I use this property to create a thermometer? That's how thermometers are built. So using PV is equals to nRT, we found out there's a relation between pressure and temperature and volume and temperature. And that's how we create a thermometer. Similarly, with resistance thermometer, we see, okay, there's a relation between resistance and temperature. Using that, can we create a thermometer? Yes, we can. And that's how we build it. So in case of this resistance thermometer, what you have is this inner working. You guys don't need to know. Essentially, what you have is you get to measure the resistance in the material. And when the resistance in the material has increased, I also know the temperature in the material has increased, right? So I basically use the notion of resistance over here. I measure the resistance in the material. As I see that the resistance is increasing in the material, I also get to know, okay, my temperature is increasing. And a similar case as above, we get to calibrate this as well, right? We see, okay, when the resistance is 10 ohm, this is the temperature. When the resistance is 20 ohm, this is the temperature. So using all of that data points, we calibrate a thermistor or whatever we're using, a resistance thermometer, whatever we're using. So basically, we are using the resistance to calibrate the temperature graph, and using that, I can find out for every different resistance in the wire, what is the temperature, right? So yeah, so what is the benefit? Again, in your syllabus, it's not included to talk in depth about thermistors or resistance thermometer, which is why I have not included it. Okay, but if you're interested, I could talk about a few extra things. But yes, what is the benefit of a thermistor? Basically, it has a larger range, and even larger than, I would say, the one over here. Based on the material you're working with, for a resistance thermometer, your range, I'm telling you, can be really large. That's the really good benefit with um, resistant thermometers. So your range can be extremely large based on what material you're working with. So there are different materials, you guys know, and based on different material, you can build different resistance thermometers. Demerit is you don't get a direct reading, so it's not like a you will read about thermocouples, right? Unlike this, and unlike your typical mercury thermometer, you don't get direct reading. You need to do a bit of calculation, but obviously you have in electronics, you can obviously automate the entire process, and you can get the temperature reading very easily. So I mean, it's not as valid, but sure, if you're manually doing it, yeah, it's not going to give you a direct reading. You need to process the data. As explained, what do? You take the resistance reading, you see how the resistance changes with increasing temperature, and based on each of these resistance, you measure the temperature. For 10 ohm, I see, okay, it's 35 degrees Celsius, and probably for 20 ohms, the temperature probably is, let's say, 45 degrees Celsius. So once you get the data point, you get a graph, and based on the graph, you get to predict other temperature. So now if the resistance has increased to 100 ohms, now you, based on the graph you have plotted, you can predict the temperature similar to this. Okay, so that's the main conceptual understanding. We take data points based on some property. What is the thermometric property over here? Resistance. So you guys sort of get the hang of it, that what is my thermometric property, right? So based on that resistance, based on whatever my thermometric property is, I relate that to temperature. I take some data points of known temperature, connect that using a line, and I find out the temperature for unknown data points. Let's say if I have predicted using 10 and 20 ohm, I can now find 35 ohms or 100 ohms. That is how it works, right? But yeah, that is pretty much it. You guys don't have much in details for resistance thermometers or thermistors in general. In case of thermistor, it works quite the reverse. So as resistance decreases for increasing temperature. You guys, where will you guys study? Uh, this is not extensively in circuits, but it has been, I guess, in your AS exams to an extent. But yeah, that is how thermistors work. For increasing temperature, your resistance decreases, right? So it is a bit opposite to resistance thermometer. So don't use the two words interchangeably. Both are very different things. Okay, fair enough. Now, in case of the last one that we have, thermocouple thermometer. What is this? Basically, now for this, I'll tell you guys. You guys will see multiple different diagrams for thermocouples, and as far as I know, this this question also doesn't come in your paper as much, but you will also see another type of do I remember it? Yes. uh, I'm just drawing another type of thermocouple that you guys may come across. I don't know which one you guys have seen in the book and other places. It is most likely this. It'll be okay. So this is another type of diagram that you guys may come across. I'm pretty sure it's this. Okay. So there are multiple types of thermocouples that you will come across. Just so that you don't get confused in the future, whenever you get a different diagram, I just drew this one as well. So just for your sake, so you don't get confused. But what is the main idea? I'll tell you guys what the main idea is for a thermocouple to work. The thermometric property over here is EMF. What does that mean? Basically, we have something to do with electricity. What do we work with? Electricity, right? So when I have mm, a thermocouple over here, if you want to, this is again not in details in your syllabus. So I'll first tell you what you guys need to know. The first thing that you guys need to know is we have thermocouple, and we calibrate this by having two junction. One is so one could be a cold junction and one could be a warm junction, and one of the points we keep changing, so we get a temperature gradient, and due to that temperature gradient electricity flows. So essentially what happens is, over here I give a known temperature. Okay, so this remains constant, and this portion, what do? We put in the place you want to measure. Okay, is that clear? So this is the one I'm using to measure different places. And these two metals, these two wires are made out of different material. And that is essential to a thermocouple. I'll explain why. So essentially what happens is, due to this having, let's say, unknown temperature, I know that, right? Let's say it is 25 degrees Celsius, and this one you don't. This one I put it, let's say, in a cup of water, right? I put it in a cup of water, and this I don't know the temperature of, and let's assume this temperature is 100 degrees Celsius. Now, due to due to these two having a certain difference in temperature, these two having a certain difference in temperature between these 2 points, it allows me to have, yeah, I drew it wrong over here. Sorry, my bad. A voltmeter. So yeah, due to these 2 points having a difference in temperature, what happens is there's an EMF. There's a difference in amount of electricity flowing. Okay, due to a temperature gradient being existing over here, we have electricity moving from a warmer region to a colder region. Okay, that is essentially what's happening. That is essentially what's happening. Due to a temperature gradient, even electrons want to flow from a warmer region to a colder region. Due to that flow of charge, what do we have? We have electricity. And due to that electricity, we get an EMF. And that is how I calibrate for different changes, different change in temperature, different EMF. So compared to this point, if I use this point, put it in multiple different places, what happens? My change in EMF is different. So I probably put this point from zero, not zero, let's say 30 degrees to 100 degrees. What happens? The amount of difference in temperature, if it's 30, what is the delta? 5 degrees. If it's 100, what is the delta? What is the delta? 75 degrees. Do you see there's a temperature difference over here? Yes. So between 2 points is a temperature difference. Whenever you have a temperature difference, you have a potential difference. Electricity or current wants to flow. Charges want to flow from a region of high temperature to a region of low temperature. That is why you have an EMF. That is the concept behind the thermocouple. So if you're confused about why we have thermocouples, how it works, that is the reason. You have a difference in temperature and current wants to flow. And you measure that. If you have a larger difference in temperature, EMF is larger. Hence, this is the plot you get. And the bad part about this is it's a non-linear increase. So it's not that if my difference is 5 degrees between 2 points, I get, let's say, a linear increase. And if it's again 5 degrees of difference, so 10 degrees of difference, you would assume this to be another, let's say, 5 volts. difference. But essentially, that doesn't happen. It keeps increasing as the temperature increases. So EMF has an increasing gradient as it relates to the temperature. So as my temperature increases, EMF increases with a increasing gradient. Okay, increasing rate, which is why it may come across in a demerit that, I'm trying to erase this, that EMF has a non-linear relation with temperature. Okay, but it does work and we use it. How we use it? We have a known temperature and we have an unknown temperature. Whenever there's a difference in temperature, electricity flows. Whenever temperature is larger, my EMF is larger. Whenever the temperature difference is larger, EMF is larger. Temperature difference is less, EMF is less. Even less, even less. Do you get the idea? Yeah? Any confusion about this portion of EMF? Often I do come across students being confused about this part. They don't understand why electricity is related to temperature. With thermocouples, especially. That's why I'm asking again. Are we are we clear on the thermocouple part? Okay. Are we good with thermocouple? Okay. So that is all you need to know. Whatever you need to know, I've explained. There's nothing more in your syllabus with thermocouples. I would get into more detail if it was, but it's not. I've looked in quite a bit. Even this, whatever I'm showing, it's a bit extra. A lot of it is a bit extra, just so that we cover all grounds. Okay, and the last thing that's mentioned in your book, this is not something I'm at all interested in discussing because this is very boring, but it's simply just remembering the information. But I'll also tell you, this doesn't come as much. It may come. So essentially, what the book is talking about is with a resistance thermometer and a thermocouple thermometer, what are the differences and why you may prefer one over the other. So basically, if you have a resistance thermometer as compared to a thermocouple thermometer, it is way more rigid, more durable. That is, the resistance thermometer is way more durable as compared to a thermocouple thermometer. As you've seen, thermocouple thermometer is basically a bunch of wires, right? That's how we measure different junctions or different points, and we get a temperature gradient. With respect to range, which one has a larger range? Thermocouples have a larger range. Do you know why? Because in case of thermocouple thermometer, electricity, flow of electricity doesn't really have a limit, do we? We can measure any amount of current, any amount of change in potential difference. It is not a problem. It is not a problem at all. In case of when we were talking about mercury thermometer, what was the limiting factor? The length of the body of the thermometer. Isn't that right? So this body itself is the limiting factor. If I had a larger thermometer, sure, I could measure a larger expansion of mercury. But that's not the case. Now, similarly, with volume of gas thermometer, same limitation. I have a height over here that I need to measure to find the pressure and hence the temperature. That's a limiting factor. So with thermocouple, since I am just measuring against, what do you call it, the flow of electricity or the potential difference between 2 points, that is how essentially we get to find the temperature, right? So that doesn't really have a limit, does it? Which is why it works. Now, in case of thermistors, uh, it has a bit of a narrow range. In case of resistance wire, it has a bit of a wide range. What this really means is there are types of resistance thermometer. There's thermistor, and there is one where we simply, the one I explained to you guys. Which one did I explain? This is most likely a part of a thermistor. But anyways, you can measure the resistance based off of wires. So let's say I have a wire over here, and I can measure the change in resistance of this wire, and I can say, okay, As the resistance increases by certain amounts, the temperature increases by a certain amount. I can also have a thermistor, which is a bit more of a complicated device. And as my temperature increases, my resistance decreases in case of a thermistor, which is a opposite relation between temperature and resistance. Okay. So different materials will exhibit different property. Now, with size, resistance thermometer can be larger than thermocouple, has greater thermal capacity, so is lower acting. Sure, you can say that. That's the thing that you can say. Why do I say that? Because with the resistance thermometer, sorry, yeah, resistance thermometer, the wires, especially the one I've seen more, I guess, talked about. In those cases, due to having a larger resistance, because of the material itself it has a high amount of thermal capacity. Or you guys have just learned about specific heat capacity, those topics, right? So you guys know that with something that has a higher thermal capacity or specific heat capacity, it can it can take in more energy for certain increases in temperature. So to go from 0 degree to 1 degree, it can take in way more energy. So it has a higher thermal capacity. That is what essentially it means. So what that really means is it will be slow process for gaining in temperature. Do you understand why it's slow process? Because notice if I have my environment, or let's say a liquid in 37 degrees Celsius, okay, and I have a thermometer, resistance thermometer, and this resistance thermometer is doing what? It is I'm using this to measure the temperature of this liquid. And what I see is it is taking way too long to reach 37 degrees Celsius. Why is that happening? Because its thermal capacity is really large. Okay, so it needs a lot of energy to reach this same 37 degrees. Okay, so as compared to, let's say, mercury, it will require very little energy to reach this same 37 degrees Celsius. Okay, so that's the thing over here. So that's one. So essentially, the size is bigger. Those are the things that we've talked about. Sensitivity, this you can talk about. This is the last thing, which I would say somewhat important. Thermistor, high sensitivity over narrow range due to it measuring temperature, measuring electricity or flow of electricity, we can be way more precise due to measuring potential difference depending on the quality of the right. This is I'm talking about this one. My bad. Not this. So depending on the type of material you have chosen, you can measure the you can measure the EMF very precisely. Okay, so when you have better material, better setup of a thermocouple, what really happens is the measurement for the EMF is very precise. Is very what? Very precise. So the temperature recording that you get can be accurate. But that is what have they said? Based on the metal you choose. That is why I'm sort of flag posting this idea of what material you choose, what kind of wire you have chosen for the thermistor. Sorry, thermocouple. I keep changing the words around. But yeah, for a thermocouple, the kind of wire you use is very important because based on that, the sensitivity will change. So if you're using the right setup, you're using the right material, it can get a very precise reading for the change in temperature and hence the potential difference. So the type of material matters in case of what? Thermocouple. In case of thermistor, it in general has a high sensitivity over a narrow range, and the resistance wire will have less sensitivity. So in case of thermistor, again, I'm explaining this. Thermistor is a different setup, and resistance wires are a different setup. Resistance wire are the typical that if resistance increases, my temperature will also increase. That is the relation. That is resistance wire. The one I talked about over here. Over here. In case of a thermistor, which also works on the basis of resistance, it is inverse relation. When the temperature goes down, resistance goes up. It's an inverse relation over there. Okay, so it's different in both cases. So yes, this is the distinction between thermistor, resistance wire, linearity. Well, EMF you just saw with the graph with thermocouple that it's a non-linear relation, right? So not a linear relation, not a good uh, indication over here. The reason I say that is with linear properties, you take a bunch of data point and you can draw a line and it becomes easier. Based on 2, 3 data points, I get to predict what the temperature is for different data points. With something that is non-linear, what do I need to do? I now need to calibrate the entire range of temperature so that later on, when I put the junction in an unknown temperature, I can easily find out using the graph. Using the graph. So over here with thermocouple, the issue is it is a non-linear relation. In case of again thermistor, what happens? It's a fairly linear relation over here, and with resistance wire, good linearity. And I was going to say this with resistance wire as well, specifically thermistor, although they're saying fairly linear over narrow range, it is different for different thermistor. Because when we work in labs with thermistor, the graph it produces sometimes can be a bit non-linear from my experience. So thermistors, working with thermistor, it is a bit of a different case. Okay, it's a bit of a different setup entirely, as according to resistance wire. Resistance wire, we work with probably uh, a set amount of range of temperature, and we don't really use it as much. We always go to thermistor because the range can be varied quite a bit, and it's more useful for electronics and all that. But anyways, for resistance wire, what happens is whatever range I'm working with, it's a linear relation. So as the resistance increases, I see a linear increase with the temperature. But whenever I'm working with thermistor, I'm saying it with my experience, uh, while measuring some extreme temperatures or extreme ends, I see a bit of a non-linear tendency towards the end of it. But it is also due to the fact that I'm covering a larger range with thermistor. So both has its pros and cons over here. Is this necessary for you to know? Well, sure. I mean, I'm just telling you guys. So in case you're confused about what a thermistor is and why a resistance wire is different, I'm just sharing it. I don't think questions around this will really cover the paper. But yeah, that is essentially the important bits between the differences of a thermocouple and a resistance thermometer. We've gone through all the types of thermometers, right? And until this point, if you're confused about any of the thermometers, any of the type of thermometers, let me know. Okay? But yes, they don't come as frequently on your paper. Max to max, they'll ask you what temperature is defined temperature. All right. So till this point, what you guys have studied, you will have heard of a Celsius scale. What is that? So the typical scale that you see on thermometers, that gives reading from 0 to 100 degrees Celsius. That is a Celsius scale, right? Now, this was figured out based on the properties of water. If you guys know this from your teachers, they may have discussed this. So back in the day, they did a lot of atrocity with science. So back in the day, what they thought was, okay, I have water, and I have this water changing its state in different temperature. So they saw that when it's really, really cold, the water freezes, or at a certain temperature, the frozen water or ice melts. So this is one state change they saw. And the other state change they saw was water apparently boils, right? So they saw that water also boils, but at a much higher temperature. What did they do? They were like, okay, so at a lower temperature, let's consider this to be zero, which is the temperature at which ice melts or water turns into ice. They classified that temperature as zero. So based on water, they created a starting point for temperature, which is 0 degrees Celsius. And they created another, which is the boiling point. And they said, okay, my water turns into gas. This must be 100. So they know 0 and 100 as the two extreme numbers, and they attached it to water or the temperature of water. So that is how the Celsius scale came out to be. It has nothing to do with science. It was just arbitrarily decided by a bunch of people back in the day. So this is the Celsius scale based on the properties of water, based on the melting point and the boiling point. Now, uh, the thing with this is, if you guys know, the boiling point or the melting point of ice, if I change the pressure, also changes. Okay. So when I change the, let's say right now, when you see ice melting at 0 degrees Celsius, what you also have to say is what is the room atmosphere pressure? If my room atmosphere pressure is 1 atmospheric pressure, then yes, makes sense that ice melts at 0 degrees Celsius. Okay. If the pressure is larger, let's talk about the boiling point. What happens? It will take a larger temperature or more energy for the water molecules to evaporate or boil because the surface tension pressure caused by atmosphere is larger. So if my atmospheric pressure is larger, what happens? I also need more energy to escape. Boiling point increases. Do we get the idea? So my pressure over here is also related. Okay, so the pressure over here is also related. Now, that relation is with respect to physics. But the way they found out 0 and 100 has nothing to do with physics or maths. They arbitrarily put these values. So if they now want to relate Celsius scale with changing pressure, they can't because these are not the true numbers of temperature. This is a completely different scale. Okay, so this is why essentially we have something different called the Kelvin scale. Okay, this is the innate property of materials. And this is where we attach the original value of temperature to materials. How do we do that? Because it's scientifically found out. So the Kelvin scale, we also call it the thermodynamic scale. Okay, so this is based on the thermodynamic principle, and you will learn about the laws of thermodynamics. Very famous. Okay, so the Kelvin scale does not depend on property of any specific substance, unlike the Celsius scale, which depended on the melting and boiling point of water. Okay, so in case of Kelvin scale, did I teach you guys today towards the beginning of the class that temperature is a measure of kinetic energy, right? So if that is the case, we can also relate my Kelvin scale to that. So I have to find out the temperature by measuring kinetic energy because temperature is directly related to kinetic energy. So my value of temperature should come from kinetic energy itself, by a measure of kinetic energy, not by the melting or boiling properties of water. Okay, so I have to relate somehow the kinetic energy to find the true values of temperature. Okay, and which is the Kelvin scale. So the Kelvin scale takes this property into account, that is the kinetic energy. And that is also why we come across the formula. I share with you guys Ke, kinetic energy, is 3 by 2 kT. You will learn about this probably next class with me. And this is essentially how you find the temperature. This is how you find out the temperature. You see, if I make temperature the subject, you will see 2 by 3. This is essentially, if I make temperature the subject, this is the equation of temperature. So I have related using the equation, using kinetic energy, I've related it to temperature. So whatever 2 by 3 kinetic energy by Boltzmann constant gives me as the temperature is the true temperature of any material. Okay? That is the true material of, sorry, the true temperature of any given material. Right? Now, I want to ask you guys something. What happens when my kinetic energy is zero? According to this equation, what do you think? If my kinetic energy is zero, what will be the value of temperature? You can put it in Slido or just unmute and tell me. What is my temperature if kinetic energy is zero? So zero energy in the material in terms of kinetic energy.
Temperature is also zero.
Exactly. So based off of the equation itself, you can say when my Ke is what? Zero, temperature is also zero. I mean, you will learn this equation. I will teach it to you guys later on. It is an ideal gases. Yeah, it is an ideal gases. Next topic. So according to this equation, what do you understand? That when Ke, kinetic energy, is zero, my temperature should also be zero. And what does kinetic energy being zero mean? Everything is static. The world is static. Universe is static. No velocity, no movement. Absolute zero. This is where absolute zero comes from. Right? So absolute zero or zero Kelvin, this is the Kelvin scale. The zero that you found out by putting Ke being zero is the Kelvin scale. It is the temperature at which there is no internal energy. And I will discuss what internal energy is later on again. Don't worry. So essentially, when everything is static, no velocity, no energy, no internal energy, that is zero Kelvin. Temperature is absolute zero. And how did we find this scale? This value by equation. Okay, so we have related the innate properties of this universe to find out the Kelvin scale. This equation, how we come across, again, I'll show it to you guys. And how do we convert between Kelvin to Celsius? Simple. 0 degrees Celsius is minus 273.15 Celsius. So 273.15 Kelvin is what? 0 degrees Celsius. This conversion, guys, please be used to. Very necessary. You need to be able to convert between 0 Kelvin to Celsius. I mean, not 0 Kelvin, any amount of Kelvin to Celsius. Ideal, most cases, I'll just even tell you guys that most of the cases you will have to convert to 25 degrees Celsius to Kelvin. This is what mostly you guys will have to do. So be used to this. Okay. Why? Because this is the room temperature. A lot of question, yeah, room temperature. A lot of question will give you that the room temperature is 25 degrees Celsius and solve this problem. So in that case, you can't use Celsius. I'm telling you guys off the back, you guys have to work with Kelvin always because Celsius has nothing to do with physics. If I relate kinetic energy and temperature, and over here you put in Celsius, wrong answer. Kinetic energy is not related to the Celsius scale. It is related to the Kelvin scale. Okay. Why? Because we got the Kelvin scale by this relation. So only Kelvin will make sense over here. Okay. So you guys need to make sure that the conversion, you're okay with it. You should be okay with the conversion between Kelvin and Celsius or vice versa between Celsius and Kelvin. It's simply 273.15. That's a conversion, right? You understand this, you can understand everything in terms of conversion. Great. What do I have? Okay. Now, have you guys ever heard of the triple point? Probably, probably not. Not sure. So, with the triple point idea, what really happens is this is essentially a point where, for let's say water, it exists as three states altogether. So, this point is basically a culmination of pressure and temperature at which water exists as all ice, water, and water vapor. So when the pressure is 0.006 atmospheric pressure, and when the temperature is 0.01 degrees Celsius, this liquid, that is water that we're talking about, will exist as all ice, water, and water vapor. And every material, based on whatever material we're working with, will have a certain triple point. Okay. Now, I say that, but not that's not 100% true. Actually, not it's not necessary that all materials will have a triple point. Water is actually quite the unique uh, sort of liquid, let's say, material, let's say. So, in case of water, if this is the graph, you guys don't have this in syllabus. We actually studied this in university, but the gradient for what do you call it? Other liquids look like this. So this is not how other liquids look like. This is how the gradient of water and ice boundary looks like. So it's a positive gradient between ice and water. That's how we describe it. But this is not a your syllabus, but I'm just saying if you guys wanted to know. But yeah, water is quite different in nature as compared to other material substances that we have. But yeah, for you guys, I need to explain what triple point is. Triple point is simply that whatever I just said. It is a certain culmination of condition that is 0.00. You don't need to remember the data. You don't need to do that. 0.006 atmospheric pressure and 0.01 degrees Celsius. At these condition, the liquid water exists as all ice, water, and water vapor. That's essentially where all you guys need to know about triple point. Okay, great. So if you guys understand what a triple point is, I'll move on. Any question up to this point? Then we have something very important. But yeah, any question up to this point? Whatever is necessary, I've sort of shown to you guys. If you guys want to know anything in more details, do let me know. But yeah, hopefully no question till this point. We've discussed sort of simple things. Okay, fair. I see no question. Good, good, good. Okay. Now, this is important. Important. Will definitely, most likely, in one of the variants, depending on where you guys are doing the classes from, will come in your paper. And this, I guess, heat capacity you guys sort of know. So we will be done with the temperature chapter today, which is good. Is my connection unstable? Oops. Hope not. You guys can see my screen, right? Yeah. I'm hoping there's no internet connection issue. Give me a thumbs up if you can see the screen. Oh, thank God. Okay. Okay, good, good. So yeah, again, this is the important bit, energy with changing states. Why is it important? Conversations about this on your paper will definitely come. And up till this point, I have reiterated one thing, that kinetic energy is related to temperature. Okay, is that clear? That's something I have repeatedly mentioned through today's class. Now, for kinetic energy in particles, when does kinetic energy increase? I've said this several times. When temperature increases. What happens when kinetic energy increases? Although the distinction is not as important, I'll still say atoms can vibrate left, right, up, down, any direction. And this is an indication that kinetic energy has increased. Or atoms can also rotate, which is rotational kinetic energy. Okay? There's translational kinetic, translational, rotational, and vibration and vibration, right? So yeah, essentially there are a couple of things that a particle can do. And if you study physics later on in life, you will hear of degrees of freedoms. So these rotation, vibration, translation are basically the degrees of freedom of an atom. It can be a solid, it can be a gas. The degrees of freedom change with different materials. I mean, different states, sorry, not materials. So for liquid, sorry, for gas, degrees of freedom is more. That is, it can move around way more. Option to move around, it's way more. And this relates to something called entropy. Why am I saying this? No reason, not related to you guys, in case any of you guys are interested. I just mentioned it. But yes, what you guys need to know is kinetic energy of a particle essentially is increased as you increase the temperature. And what does it do when temperature increases or kinetic energy increases? It starts vibrating more. Now, potential energy in particle. Have you guys studied right now with me gravitation? Yes. So with the gravitation topic, you guys have studied or understood that with this graph, if you guys have seen and remember, as I bring two objects closer together, their gravitational potential increases become gravitational potential energy becomes more negative. Attractive forces grow stronger as you get closer to two objects. So if I have object, why do I keep drawing a heart? uh, okay, so essentially speaking, if I have this object over here, it's far away, the gravitational potential energy is less negative. Notice this graph. If my separation between two masses, two objects, have increased, the potential energy between them is more positive. In the sense, it is closer to zero, or it is higher. Potential energy is higher. You can technically say that. You can get confused and say, isn't it higher over here? Well, no, it is more negative over here. Technically, it's not higher at close distances. So as you get closer, it gets more negative. So it has lost energy in the process of coming. And I explained it in gravitation for two classes that why it is negative and why it loses energy. Basically, due to the attractive forces between in gravitational fields, we study that if two objects exist, there is a force of attraction between those two. That is the law of gravitation. Two objects exist, they attract each other. Any mass, any two masses. So if there is some sort of attraction over here and they pull each other together, and I push this object, the highlighted one, away, then I have transferred my energy to the object, right? I have transferred my energy to the object. And what happens is this energy that I have transferred, this must be lost as it comes closer to the attracted object. So as you come closer to any object, what happens is you lose energy. This is the proof because I transferred my energy to the object to push it away. So what will happen if it comes closer? Simple intuition says it must lose that energy, right? So that is what happens. As it comes closer, it keeps losing energy, right? You notice this? As it comes closer, as the separation decreases, keeps losing energy, or potential energy becomes more negative. Okay? So what we say, what we say is when separation between atoms decrease, potential energy decreases. And as separation between atoms increase, as separation between atoms increase, potential energy increases, moves more towards zero. That is an increase, my friend. Okay? That is an increase. So potential energy of particles depend on the distance between the atoms themselves. Okay? I hope that much is clear. And this is very related to the gravitation topic you guys just studied. Okay? So if you just remember that really well, it's easier to understand. So the potential energy increases to zero at infinity, which is a theoretical concept. But when I completely separate two atoms, so if I have an object over here, right, and I have atoms over here, they're very close. They have a low potential energy, very little potential energy, or I mean, it has a very negative potential energy. And as I push the atoms away, that means I've given some energy to the object, I mean, to the atom. It has gained potential energy, less negative now. And as I keep pushing this atom away, as I provide that energy, it reaches zero at infinity. So if I put this object, so not object, why do I keep saying object? If I keep pushing this atom really far away till infinity, let's say till infinity over here, this is not infinity, of course, but if I push it to infinity, the atom to infinity, its potential energy increases to what? Any guesses? Zero. 0 joules. You see this graph? So as I increase separation, potential energy increases to zero. And it's free. And when it's zero, it's free. It's under no gravitational field, under no attraction. Okay?
All right,
Great.
sir. So even in gravitational fields, like related, I wanted to ask this: at
Yeah.
infinity, does that particle have more energy than it would have at like the points closer to another
At
particle or
infinity,
mass?
it is free. It has nothing. It is a free particle. It is simply zero energy.
Like
Yes, in
stationary?
comparison, now, yeah, what you're asking is in comparison to something that, let's say, in this universe, which has some sort of attraction, hence negative potential energy. So,
Yeah.
what negative potential energy really means is it has some amount of attraction. What is negative in essence? It is an imaginary concept, right? So, what uh, negative over here really means is it is simply under some sort of influence. It is being attracted by something. So, in theory, we relate that idea to having a negative potential energy. So when we say when we define gravitational potential energy, if you look at the definition, is amount of energy needed to bring that object from infinity to a defined point. Okay,
Yeah.
so if I have infinity over here, the object over here has 0 joules. So what is the energy if this is Earth? What is the energy that I need, or what is the energy that the object will lose to get to this point A? That is how we define gravitational potential energy. And what is the energy if I have to take the object from A to infinity? The same energy I have to provide to the object. So the
Right.
object now gains that energy, right?
So
So
from
now,
like infinity to A,
yeah,
is that object like it's not losing energy? Aren't we using
it is.
energy to
No,
bring it to A?
it is. So yes, you will say I have done the work on it on the object. This Earth has done the work on the object to bring it to A.
Yeah.
So this does the work, but this loses whatever energy it had to be pushed away to infinity. Now, what the interesting way to think about this, from A to infinity, did I not push this object away? Wasn't the field attracting it? So what
Yeah.
I did was my mechanical energy, I kept pushing the object to infinity. So I transferred my mechanical energy to the object. And at infinity, it becomes free, under no attraction. But now, if I pull it in and it starts falling in towards the earth, it is losing all that mechanical energy that I transferred from my body to the object. And it gets pulled. So whenever you have a pulling force of attraction, it takes all your energy away, all your potential energy away. That is in theory. That is how we explain it. Okay, do we get the idea?
Okay. Okay. Yeah.
So whatever I transfer to the object, the simple way to understand, I transferred some energy to the object, and we know that at infinity, energy must be zero. That is our reference point. That is what that is a fundamental over here. Based on that, we define that closer to any object, joules or energy is negative. So granted, we all agree that at infinity, my energy must be zero. Then we have to agree that if I push an object away to infinity, I'm transferring energy. That means there's a gain of energy of the object to zero. So if now the same object comes back to A, then energy must be lost. There is no way I can increase an object's energy to zero if at A it is not already negative. How can I increase an object's energy to zero? It is only possible if the object's energy is negative at point A. That's the simple logic over here. Okay?
Right. Thank you.
Okay, no worries. So that's how I often explain gravitation. Different people will explain differently. People will say it's an attractive force, hence negative, and that will be the end of conversation for most people. But that simple analogy of transferring your energy and increasing an object's energy to zero gives the intuition that since I'm increasing the energy to zero, then the object's potential energy closer to the massive mass must be negative because there is no other way I can increase the object's energy to zero. If I'm increasing the energy to zero, that means closer to the object, it must have been negative. So that's the intuition I try to bring in when explaining gravitation, right? Same thing over here with atoms. Greater separation, potential energy is greater. Okay? Or in comparison to being closer. So if it was closer, it was more negative. Now, if it's further away, it's increased. It's still negative, but less negative. So I've transferred some energy from my body to the atom. So now let's look at it in a bit more depth. So when the particles are close, attraction is large. And due to that, your potential energy is negative. As the separation increases, potential energy will increase to what? Zero. So yes, in theory, you can say an object which is at infinity with 0 joules of energy has more energy than the object that is closer to the massive mass. In theory, there is nothing wrong with saying that. You're absolutely bang on and right when you say that statement with this theory in mind. So at infinity, if an object has 0 joules of energy, right, closer to the object where it's more attracted, it will have negative potential energy. So it has way more potential energy at infinity. That is the right statement and a very accurate statement. So since work is done on the particle, giving it energy, increasing its P to zero. This is exactly what I just mentioned, that if an object's potential energy has to increase to zero, then at some point it must have been negative. Otherwise, I can increase it to zero. So we have said that multiple times. Now, wait a minute. So essentially now, this is the important
Sir,
part. Yeah,
when we like push something away, we say we're doing positive work on the object, right?
exactly. Exactly.
But since it's gaining energy, isn't it doing negative work? That object?
So we are doing positive work on the object, right? So
Yeah.
that's why the object gains energy,
Oh, okay.
right? So think of this, right? Even your normal concept of GPE that you guys studied in O levels, when I lifted the object from Earth, I did work on it. Wouldn't you see if this is mgh, right? So mass is three. Oh, just forget it. 1 kg. 10 is the, let's say, gravitational field, and height is 1 meter. I did 10 joules of positive work on it, right? Wouldn't you say that? It's the pretty much the same idea. I lifted it up. I did positive work on the object, and the object did what? Gained what? 10
Energy.
joules, right? That's the idea, my friend.
All right.
So when I'm working with gravitational field as well, I am providing the energy, I am pushing it away. So the Earth is attracting this object down, and I'm working against that field. And I'm giving it that 10 joules of energy to go away, get away from Earth's gravitational field. Do we get the idea?
Yes.
Yeah. So now when the object now drops, it loses that energy. So even though, yes, the Earth is doing the work on bringing the object, but it's bringing it closer, which is why it's losing that energy. So negative work is being done. So if one is positive, by default, the other has to be negative, right? And we understand why it's negative, why getting closer is negative, right?
Yeah.
Okay, great. So yes, when I started teaching this gravitation one, this is the most confusing part. This negative concept is the most confusing part. So it's good to get your clarifications in with gravitational field. And yeah, so now with state changes, this you need to understand all of this. What happens when state changes? What happens to the potential energy? What happens to kinetic energy? Again, I'm flag posting. This is a question that can come your way. Okay, so when you have state changes, let's look at one by one. When I have what happens to the intermolecular forces. You guys must have heard intermolecular forces. That is, if I have an object over here, multiple atoms inside, there's some attraction between the atoms, right? Due to gravitational fields, let's say, right? It can also be, let's say, positive charge and negative charge. They have attraction, but let's stick to the atom, right? They have some amount of attraction, intermolecular attraction, we say, intermolecular forces, right? They're bonded together, right? So if you carry that idea of forces of attraction between atoms and try and relate it to gravitational field, it will be better. You will understand what's happening over here. So in solid, can I say intermolecular forces are strongest? Yes. It is a rigid material. Atoms are closely bonded together. So the strength of bonding is larger. So intermolecular force is what? Strongest. Liquid, slightly weaker, but not too less. Why? They are still maintaining they're you know they're still occupying the same volume. They're not occupying different amounts of volume as opposed to gases as the weakest intermolecular forces because they occupy a larger area, and the amount of area it occupies or space or volume it occupies changes. So intermolecular forces very little or the weakest in comparison. Kinetic energy. What do we think? Solids will have the least amount of kinetic energy. Why? Because I get back to that idea of rotating, vibrating, translational. In solids, can the atoms in the object translate? That is, move from point A to B? No. What can it do? It can't really even rotate. It can't really even rotate. It can only vibrate. It doesn't even have the rotational degree of freedom, as we technically say. Over here, what can happen is it can only vibrate. So the kinetic energy over here in solid is the least. Okay, in case of liquid, a bit higher. It can move around. It can translate around. In gases, maximum. It can not just translate or vibrate. It can also rotate. right? And it can translate over large distances, higher kinetic energy, my friend. In case of potential energy, what do we think of solid? Most negative, my friend. Why? Because they're closest together. Related to gravitational field, I keep saying this, you will have an easier time understanding. So closer together means way more negative potential energy. So less potential energy. So most negative potential energy in case of solid. Liquid, there's more space between the atoms. So higher than solid. But still negative. It's always negative. It's always negative. Until unless the separation is infinity, which is not possible. So liquid has a higher. Okay. Okay. And in case of gas, we assume potential energy is zero. And this is a very, very important concept, an assumption for the ideal gas topic. The reason we assume it to be zero, my friend, is the gases, the atoms being as small as they are, they're really small. And for what space they occupy, the potential energy between them is pretty much zero. Think of the formula again. I keep saying this. Don't forget gravitational law. What was the formula? GMM, GM by R. So GPE, GMM by R. If I just think of gravitational potential, if the separation between two atoms, while the mass is really less and distance is really large, what do you think happens to GPE? Very little, right? Atoms have very, very little mass. It is very small. So both the separation is large and mass is little. It's not just that the separation is large, it is also that the mass we are working with is little. So see how using just the formula, you can justify so many things. Okay? So you see that we can assume the potential energy to be zero over here. Why? Mass is very little, separation is really large. So the end result of GP that you get in case of gases is almost zero. So it's a really little small negative. Oh, don't forget the negative, by the way. There's always a negative sign in GPE formula. But what I'm saying is this negative value is very little, very small, very, very close to zero. Do you get the idea? So this is why we assume potential energy in case of gases to be zero. Simple maths, right? Simple maths. Okay. So now what else do we have? Pretty much end of it. Oh, you do have heat capacity. I'll just finish this part. You probably will be left with one thing. So this is how you guys must have looked at this at some point in your life. State change graph, and this there you need to understand something very important over here, and that is notice the state changes. It goes from solid, then there's a state change over here. Have you guys heard of latent heat of fusion? Latent heat of fusion is basically whatever the heat capacity is, that is however much energy I need for 1 kg of mass to convert from solid to liquid. That is the latent heat capacity. Okay. Now it can be a fusion or vaporization. Depends on what state change we're talking about. So what happens over here from B to C? State change happens. So when I increase the temperature, when I provide the heat, so let's say I have a solid over here and I provide the heat, this heat during B to C, this energy, heat energy is going to break the bonds between the atoms. So state change is happening between B to C. Okay? So between B to C, you have both solid and liquid. Temperature remains constant. You guys must have studied this. Okay, now see what happens. State change is complete. All of the energy that it took in went into breaking the bonds. Okay, went into breaking the bonds. So from C to D, temperature rises again. Temperature rises again. And from D to E, what do we have? Again, another state change. So from the liquid to gas, again, the same amount of mass, whatever you have, whatever you're working with, is gaining energy. All the heat it is gaining is going to what? Break the bonds again and turn into gas. So low temperature rises between D to E, my friend. Why? Because all the energy coming in is only used for breaking the bonds. That's it. Temperature doesn't rise. Once all of the liquid has turned into gas, now the temperature rises again. Now, what is the potential energy and kinetic energy relation over here? Everywhere between AB, between CD, and between EF. Very important. Due to temperature increasing, do you see a temperature increase over here on the temperature y-axis? Yes, you do. So all of these cases where you have a A to B, C to D, or E to F, you have a temperature increasing. You have what? Kinetic energy increasing. Is that clear? So whenever you have temperature increasing, you have kinetic energy increasing. Okay, that's very important. What is the definition of kinetic energy? Measure of temperature. Or what is temperature? Measure of kinetic energy. So when you have temperature increasing, you know kinetic energy is increasing. Now, the separation between the material stays the same. Between the atoms in solid, solid may expand a bit, but that is negligible. Between the atom, the separation does not really change. Even in case of C to D, liquid, the temperature increases, but the volume that the liquid occupies doesn't change as much. Very little change, almost negligible, which is why we say potential energy doesn't really change. Same with gas, although with in case of gases, we already considered the PE to be what? Zero, right? So even if the separation increases, doesn't really matter. We consider the change in PE to be negligible. Okay. So between A, B, C, D, and E, F, potential energy changes? No. Zero. Kinetic energy changes? Yes. With respect to however much the temperature is increasing. B, C, D, E, what happens? B, C, and D, E, state change happens over here and over here. What happens in state change? Does the temperature change? Does temperature change? No. Will kinetic energy change? Yes. The kinetic energy will indeed. Sorry. Does the temperature change? No. I was going to talk about potential energy. My bad. Does the temperature change? No. Does the kinetic energy change? No. But does the potential energy change over here? Yes. The separation between the atoms change. How? Because you're breaking the bonds between solid to turning into liquid, right? You have broken the bonds. You have what? Broken all the bonds. So now they're more separated. They occupy way more space. Due to the bonds being broken, the attraction being less now, potential energy increases. Bonds are broken. Separation increases. This is a significant increase in separation. But the kinetic energy stays the same because temperature doesn't change. Same with liquid. In case of liquid, notice one thing. This I want you guys to understand. A to B, what is the length of this graph in terms of times per second? So x-axis I've plotted the time, y-axis is the temperature. For B to C, notice it takes less time because it takes less energy to turn from solid to liquid. Pay very much attention to this. Solid to liquid, some bonds are broken. The entire bond is not broken. They're still occupying the same volume. So the amount of energy it takes to turn from solid to liquid, less. If we're talking about 1 kg of a substance, it will take less time to turn from solid to liquid as compared to liquid to gas. Why? Liquid
Because
to gas.
gas is
Yeah,
further apart. Is it because of that? Liquid
yeah,
is
it's further apart, and we say potential energy is zero, zero forces of attraction. That's the thing. We have completely broken all the bonds,
uh,
right? So from liquid, notice from solid to liquid, only some of the bonds are broken. Some amount of bonds are broken. So we have added a degree of freedom between the transfer of solid to liquid. But from liquid to gas, all the bonds have been broken, which is why it takes a longer period of time to turn from liquid to gas. Hence, larger amount of energy was required to go from liquid to gas. This is a very, very important concept, and this is a question that can come your way. That why is the time occupied for liquid to gas more as compared to solid to liquid? Okay, is that clear?
Yes.
Okay, good. And I will keep it at that. This not too much over here. You to an extent know that. I will discuss this and the last part. This this you guys know as well. So we are pretty much done with the syllabus, but I will still go through this heat capacity and I'll show you guys a very, very interesting question. Literally speaking, this semester, this was a type of question I had to work with in an exam. So yeah, it's a pretty decent, good question, conceptual question. So this is something I'll discuss. This is something I'll discuss. And this is very little 5 minutes of content. So I'll barely discuss for 10, 15 minutes next class or 30 minutes max next class. And then we will get into ideal gases, which is very important, very conceptual, and will take up 1 hour, 30 minutes pretty much. So we're done with temperature. I mean, 99%. Just three things left, and I'll discuss this Saturday. Do we have any question today? Up till all that we discussed, I'm done with temperature pretty much. Any question today?
No.
No.
Great. Good. So we're done for today. Thank you for attending, guys. See you guys on Saturday. Okay, Saturday, same time. We're going to complete a few things of temperature and we're going to complete ideal gases. So be prepared. See you guys soon. If you guys have any question, any problem, let me know in the classroom or Slido is always open. Great. Thank you guys for attending. If you guys have anything to say, you can.
How do
Otherwise,
I
I'll end.
access
Yeah.
the slider?
Yeah. So this is the code. What you will do is basically you will search up Slido, and as you go to Slido, this is what you get. So you put in the code over there 2321508. I'm hoping this is the right code, and you immediately get to whatever poll I have. So you can ask me question over here. Type your question in. This is all anonymous. I don't get to see who's writing what. And even for the answer, completely anonymous, I don't see. So right now I have this poll live, right? And you can write your answer. So if I say, okay, answer question 12, you put in your answer over here and send. That's it.
I will.
Okay. Yeah, got it.
Yeah.
Great. So that is pretty much it. We are 8 minutes over class. Sorry to keep you guys waiting. But yeah, that is pretty much it for it. If you guys have anything else to say, you guys can. Otherwise, I'll end the meeting for today. Thank you guys.
All right. Thank you, sir.
Thank
You're
you
most
so
welcome. You're most welcome. Bye bye, guys. Have a good time.